let's start off with, that's the end of the lecture because I was reviewing stuff. I told you at the end of last lecture that I would go through the cylinder calculations at the start of this lecture. And I'm going to renege on that because there's a better part at the end of this lecture to do it. So I'm just going to postpone it till then. So we will start off instead. The reading for this one, largely it's 3-1, 6-1, and 7-1 through 7-3. This is one of the reasons we don't use the textbook as our primary form of instruction. We think that this is a better grouping of functions and modules and makes more sense than what the textbook uses, so we ignore it. Hopefully that's okay. What we want to talk about today is we're going to talk about Python functions and how functions can be applied to different data types. We saw a little bit of that on Monday when we were talking about the plus and minus, the plus and star operators being applied to strings as well as to integers and floats, but we'll talk a little bit more about that. We'll talk more about string functions and other types of functions and how functions can be called and applied to data types. And we'll also talk a little bit about some built-in modules, some built-in functionality, extended functionality from Python that's beyond perhaps the initial language definition. So let's start off with what we learned starting up. We started off last two lectures by talking about three different data types. And the data types we talked about were ints, strings, and floats. And we had things like, this was a string. Let me kind of pop over to, let's do this in Spider, I guess. So we can have something like, this is a string. Pickle Rick is the name, right? Name has Pickle Rick. We can print the name, right? Pickle Rick. And printing and asking for the value of name return two different things, or they look different. One gives you the denotations for a string, but when you print it, those are eliminated. But we can also ask it questions like, what's the length of name? Right? And, then when we get the length of name, now we count up how many characters there are. P is 1, I is 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Right, so there's 11 characters in Pickle Rick. And by the way, this is something I should have mentioned last lecture. One of your compatriots kind of brought this up to me in office hours today. What happens when we have, this is one of the, essentially one of the problems from the practice problems in strings. What happens when we have this, Pickle Rick and Morty and Summer. And I hope I'm spelling Summer right. Right? And let's actually put another space in there and we'll do that. Okay? So, and now we want to know the length of name. And if you look at this, Pickle Rick was 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 24, 28, looks like about 30 characters. So if we do length of name, we're expecting to get 30 characters, and we're getting 33. Okay, so that's not right. So let's look at name. And now we count these, and we say Pickle Rick, that's 11, slash 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 28, 32, 33, 34, 35, and 36. So if we count all the characters, it looks like the length should be 36. But again, the length is still 33. So what the heck is going on?
Does it not count the slashes?
It's counting the spaces.
It's counting the spaces, but it's not counting the slashes. And that's what the issue is. So this /n, any escape character, remember we talked about the escape characters? There's a bunch of escape characters. The only ones we were really concerned about knowing were in that little table in chapter 3. I believe it was /n, /t, /single quote, /double quote, //. I think those were the ones we were concerned about. But check out that table. This is one character. So /n is one character. /t is one character. Single quote is one character. The slash says this is a special character, and then the next character defines it. So just be careful when you're in that kind of a mode. The length of name is in fact 33 because we go 11 /n 12 21 /n 22 26. Okay, now I did it wrong. Okay, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and then the final /n is 33. And notice that because we put this triple slash on its own line, there has to be another /n at the end of summer. If we were to do something like this, the length would be 32. Of course, I didn't try this before I got to class, so I could be wrong. No. All right, so it's just something to keep in mind as we're kind of working through this, that's kind of the way, it's not kind of the way, that's the way this works. All right. And we went and we'll go through some more of these functions today.
Wait, so it counts the spaces, but it doesn't count the /n?
It counts the /n as a single character. Any escape character is a single character as opposed to multiple characters.
Oh, so it doesn't count them as two, just one.
Exactly, yep. Okay? So spaces are always counted. Spaces are characters, right? So we could do length of, and I could do 1, 2, 3, 4, 5, 6, 7. 7 spaces has a length of 7. 0 spaces has a length of 0. Right? That's the null string or the empty string. All right?
What if you didn't want to count the spaces, just the letters and numbers?
We'll get into that in a second. Okay? That's one of the string. It's a combination of string functions that we're going to talk about in just a second. All right. So let's see, where is it? It's right in there someplace. Yeah, right about in there. All right, so there are also numerical functions, right? So we have things like absolute value, power. These should be relatively understandable to you guys. They don't use arbitrary names. But let's go through a few of them. You know, absolute of -7 is 7, and the absolute of +7 is 7. So the absolute is just essentially the distance from the origin on a number line, and it works for floats and ints, right? It doesn't matter. The power function, power 3 squared, right, takes the first value and raises it to the power of the second value. And again, it works with integers and floats and combinations of integers and floats. And as soon as you have a float in there, it comes out float. By the way, for all of these functions, if you don't know how they work, there's a help function that you can type in. So you just type help and then the name of the function you're interested in. And what it tells you is how to use it, right? So this one says power takes 2 required arguments, a base and an exponent, and it raises the base to the exponent. And it tells you that, you know, it's equivalent to the operator ***. And it also gives you an optional modulo function, so an optional remainder function, if you want to do wraparound, right? Maybe you want to limit your values to 256, or you know, 0 to 255, for example. Then you would put in a modulo of 255, right? So we can go in, or 256. Sorry. So if you want your values to be between 0 and 255, and of course I didn't read that well. Oops. These have to be integers to do that. Right. So the help function is useful. Learn the help function. We can do something like help int, and it'll tell you, well, help on int, which isn't a great one because it is actually a type with a constructor. So there's a lot of functions that apply to ints. Int, float, round. Int and float we learned yesterday. We can look at round. Right? Round takes a number and then a number of digits and rounds it to that number of digits. So if we want to take x equals 1, 2, 3 dot bunch of digits, we can do something like round x comma 2, right? We can do round x, which will round to 0, x comma 4, right? X kind of, wonder what happens if we go bigger. Okay, it just stops. All right, so it doesn't pad with zeros. So these are all functions that we can kind of use. I think I've got through most of them. The idea is that there's a bunch of built-in functions that allow us to work with strings. There are a bunch of built-in functions that allow us to work with, we have min and max. A bunch of built-in functions that allow us to work with numbers. We can do something like help min, and what that's going to tell us is that we either have an iterable or we have multiple arguments. We'll talk about iterables later when we get into lists. Lists are one of the iterable types. But for now, just know that if you want to know the smallest of two values or of multiple values, you can go to, just give it a list of values, 3, 5.0, 9, minus 18, 19, right? And it'll tell us what the minimum is, and the maximum works similarly. Okay, so these are all functions that are built in that work on numbers. So the idea we want to get you is not these are exhaustively the functions that you have. There are a lot of built-in functions. We'll go through. You can go through them. I'll show you how to get all of the built-in functions in just a few minutes. But what we want to point out is that Python is a very rich language that has the ability to do a number of serious operations on both strings and numeric values. And learning these numeric values, learning these available functions is going to make your lives a lot easier as you kind of go through and generate more and more code. Okay, so where do we want to go from here? So the next thing we want to look at is how we generate functions on values. And in particular, what we want to start looking on, these are all built-in functions. Everything above this line are functions that are built into Python and that come kind of natively when you spin up your Python interpreter. That's only one of the ways that Python allows you to work with values. There's another thing called modules, and modules allow you to associate different functions, different operations that can be done on different types. And the reason it can do all this is something called, if you're familiar with object-oriented terminology, Python is a very object-oriented language, although you probably won't notice it in general practice unless you know what you're looking for. But the idea behind that is that something like, let's say, a string is an object. And what the object is it has data that goes along with it that describes its state or that holds its state. And then on the other hand, it has these methods that work on that data to do certain operations. Everything in Python is an object. An integer is an object, a float is an object, a string is an object, a list is an object. All of these are objects, and because they're objects, they have this abstraction that says this is what this thing is. This is what an integer is. An integer is a whole number, and it has operations defined on it like plus, minus, exponentiation, etc. Float is an object. It has certain operations, certain properties. A string is an object. It has certain operations, certain properties, and they all have data that go along with them that describe the current state. So, if you remember back at the last class, somebody asked me about, how is this stored? And I kind of gave a little bit of a wishy-washy answer because strings can be stored however they want to be stored. They're an object. They have data and they have operations that work on the data. So, as long as they meet the abstraction of what a string does, as long as the operations you're expecting on a string work, it's not up to you, it doesn't matter to you how they're actually stored or what data structures the person who generated the code uses to implement that particular object. So this is the idea of abstraction, and that's something that as we go through the semester is going to be very important to what we try to accomplish, because whenever you get into a big programming problem, the idea is abstract away as many details as you can, figure out, maybe we'll do a Pokemon thing, what operations define a Pokemon, what data do I have to carry along to be the Pokemon, and then code that up separately, and then just use it in your main program to allow you to accomplish the things like walk the Pokemon around a grid, or throw a ball and catch them, or whatever it is we end up asking you to do. Okay? So, anyway, each object defines an organization and structure to the data they store. Integers, for example, can be arbitrarily long because they're not storing just a computer memory worth of data, right? They are storing it somehow a little bit differently. Right, so they can get really long. That would overflow any integer type in C or C++, for example, by a lot. It's pretty easy to get big numbers if you just use a little bit of exponentiation. I'm not sure I can find the end of it. There we go. Okay, so there's the beginning of it. It's 1.5 times 10 to the something, effectively. All right. So when we have that, then we can start thinking about how we actually use these abstractions, right? So when we're using integers and strings, we kind of ignore this part. But they're there. So for example, and I should have tried this, 5 dot add 7. Okay, so this is actually the same as there was a parsing problem because it didn't know what type. Well, there's a parsing problem because 5 could have been a float or or an integer, and it didn't know what. It couldn't parse it. It couldn't parse that thing. But now it knows that x is an integer, so you can do x dot add 7, and that's the same as x plus 7, right? So this is how you could express the addition operator using this module notation. So let's talk about this in a little bit more detail. If you have an object, and we can define objects. We'll talk about defining objects as we go through this class. If you have an object and you want to call, sorry about that, hold on just a second. Okay, so if you have an object and you want to call a method of it, right? Like, so we have the object x, which is of type integer, and we want to call the add function on it. It's object, right, x, a dot syntax, and then the function you want to call. and then followed by any arguments relative to the function. And we'll get into this more when we're talking about actual generating modules on our own. But this syntax pretty much works for any type of module. And one of the modules that's important to us is strings, and strings have a lot of functions that are defined on them, and they're all built into the definition of the string variable. So let's kind of work with this. We're going to ignore our integers for a bit, and we're going to kind of move over to using strings. So for example, if we have good morning, makes more sense. This doesn't look like an addition operator. It doesn't look anything like this. So let's use some things where it actually kind of makes a little bit better sense. We'll start out with B equaling good morning. And now what we're going to want to do is, let's say we want to find all the O's in B, or we at least want to find one O in B. So we can do B. I told you that there's a help function. We can do help on B, since B is a string. This may have changed from before, but now we can do help on string. It used to give you all the help. I just installed the newest version, so maybe that's what's going on. But it used to give you help based on the type of the value. So since B was a string, it would have given us help on string. We can do help on string still, and it tells you all the things that you can do with a string. This is very good for you to know if, for example, you're working on a homework and you can't remember how to do a strip, which takes things off the edges, or you can't remember how to, I don't know, make it uppercase or lowercase, which is what I was looking for, or how to replace values and get rid of them. Anyway, help string will tell you how to do that. One of the things we can look at is help string.find, right? And what find does is it takes a string S, right? That's the string S out in front. And it takes a substring. And it takes some optional parameters consisting of a start position and end position. We'll talk about that in a second. But it returns where within that substring, where that substring is found within S, subject to starting and ending criteria. So anyway, it's much easier to show this with an example. All right, so B is good morning. We can do B.find, and we can give it a substring. In this case, let's look for an O. We could look for OO. We could look for OR. Let's look for OR first. Right, so B.find OR will tell us it's at position 6. So if we count here, good is 0, O is 1, 2, 3, 4, 5, and then the OR starts at position 6. And remember, I started counting with 0 because strings are all strings and lists and most of the iterable containers in Python all start with 0 instead of 1. So if we were to look for example, the G, that would be at position 0, right? 0. All right. Well, we know where the OR is. Let's look for the O. O comes up at position 1. Now we can use the count function to find out how many O's there are. So we find out there are 3 O's in the word. And if we want to find out where all of the O's are, we have to kind of walk through using our starting and ending criteria. So we can do this bfind O. It tells us it's at position 1. Now we can say start at position 2 and find the next O. Right? And that finds it at 2. Right? So if you look at this, 0, 1, 2. And now we can do it again, this time starting at position 3 and find out that it's at 6. Right? If we want, we can also put an end on there. Let's say we don't want to look past position 5, and, well, that returns a -1 because there are no O's from 3 to 5, right? 0, 1, 2, 3, 4 is the space, and 5 is the M. There's no O's in there. It won't find it. If, however, we were looking for the space, it would find it, and it would find it at position 4. Okay, so that's kind of a little walk through one example of calling a function that's defined on a specific type of object, in this case a string. We could have a little fun with this. Oh, by the way, I put b into a string. You can do this with the strings themselves. Right? You don't have to put it into a variable. It works with literals as well. Okay. And there are a lot of other string functions that kind of work similarly. So today is the day I should have worn my Pluto is a planet shirt, or my Revolve in Peace shirt, because we have Neil deGrasse Tyson, who was one of the people responsible for deciding that Pluto is no longer a planet. And that was immortalized in Rick and Morty, by the way, too, just in case you're a Rick and Morty fan. Okay. I swear I copied that. Okay. Spelling Neil deGrasse Tyson is beyond my easy things to do. Okay, so
There are some things not meant for mortal man.
yeah, exactly. So anyway, we have name. Name is Neil deGrasse Tyson. We can come in here and we can do some things just to manage the case. So, for example, if we want to convert this all to lowercase, right, we get rid of the capital N and the capital D, right? That brings out Neil deGrasse Tyson. The thing to keep in mind is that doesn't actually change name. All it does is it returns a new object of type string with everything lowercase. So our name is still the same as it was. If we actually want to capture that, we have to do something like put it into lower name, a variable, right? We have to assign it to something. And now name is still Neil deGrasse Tyson, but lower name is Neil deGrasse Tyson, or Neil deGrasse Tyson. I don't know, however you want to go, lower versus upper. Anyway, you get rid of the N, capital N, make it a lowercase, capital D, and capital T. And there are other things that work here too. We can do lower name dot upper, which converts everything to uppercase. We can do lower dot capitalize, which brings it back to the very first letter gets capitalized. We can do lower name dot title next. Yeah, I don't want to skip any. Dot title, right, which capitalizes every after every space gets capitalized. So there's a lot of things we can do with this. One thing I want you to notice is that every time we return, we return something that's still of an object of a specific type. These all return objects that are type string. Count returns an object that is a type integer. Find returns an object that is of type integer. So if you want to do something like, back to our B again, if we want to do B, right? If we want to do B dot find O plus or times, let's go do it times, B dot count right. These are both, that's not a good one. Let's do plus. B dot find is giving us a 1. All right. So, if we want to do something like B dot find O plus B dot count O, these are valid types, valid objects of type integer, so they can be used in expressions just like any other integer. And similarly with our well, I'll show you the other ones here in a second. Yeah, we'll do that with the replace. And that works with strings too. So I'll show you that with this replace here first in just a second. So let's say we have, and again, I'm going to cheat and actually copy this. Okay, so we have a word abracadabra, right? Our magic phrase. If we want to do something like we want to replace the string br with dr, I guess. At least that's what's in the notes. Comma dr. Right, we can do that. I'm going to do something like somebody asked me about spaces, by the way. How would you count everything but the spaces? So now that we know how to do
Yeah,
this,
I asked that.
yeah. So now that we know how to do this replace, right? We have name is Neil deGrasse Tyson. We have length of name being 19, right? So 5 to here, 10, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah. 10 to there, 15 to there, and then another 4 for the end. Right, so the length is 19. If we want to find out how many it is without spaces, we can kind of do length name dot replace, and then replace our spaces with nothing. Right, and we'll come out with 17, getting rid of this space and this space. Okay, so you can pop these. This is a valid string. This valid string evaluates to Neil deGrasse Tyson without the spaces, and you can pass that in either like this or by assigning it to a variable. You can pass both of those into the length function. See, we can do abracadabra dot replace, and we can get rid of all the A's. So it doesn't only work with spaces. We can get rid of A's. I think we've done the count, so I'm not going to do the count. We've done find a couple of times, and I showed you what happens if you can't find it. Like for example, if we do name dot find x, right? There's no x in Neil deGrasse Tyson, so that returns a -1. I think the rest of these we've pretty much gone through. Yeah. So, basically this is the format that you need to know. You have a string, or you have an object type. We've been using strings. I showed you an integer example earlier. Dot, so name, right, type string, dot, some function, find, and then any arguments that function needs. Let's say we're looking for a space in Neil deGrasse Tyson. We would find the first one at 4. And then we could also go through and kind of find the next one by skipping ahead past 4. All right. And despite us telling you this, there are ways, like we saw with the int, right? We did x is 5. Nope, x is now abracadabra. X equals 5. We did x dot add 7, right? This is an equivalent to x plus 7, right? And similarly, we can do something like name plus exclamation point, right? So this is a different form. This is still a function on type string. It's something defined on the object type string that does a concatenation, right? The string addition. So it has a different form, but it's it's still a function on strings. And by the way, I haven't tried this, so this may not work, but The add function, this plus, is just a special function that's kind of defined like that. We'll get into that when we get into modules, writing our own modules a little later. But these are all tied together. They're all the same thing. We have modules, and we have things we can call on the modules, and sometimes they look like this, and sometimes they look like, this. So, exposing you to the ideas early and often. All right, let's take I'm going to give you a couple minutes to go through these practice projects. Let's go to 325. I don't want to take too long on that, but I think we can do that. And then we'll go to 323, and then I'll walk through a couple of them, and we'll waste a few more minutes on that. So yeah, go ahead and take, kind of take a look at those and see what's going on, and let's see. 1 is boring. I'm not going to do 1. If you guys need me to do 1, I'll do it. 2's kind of fun, although we already kind of did 2. I'll do 3. I'll do 3. 2 is essentially what we did. Up here someplace. Here, right? So yeah, go ahead and do that, and I'll give you a few minutes. All right. I think, like I said, I want to go in, and I don't want to do all of these. I will do them if you guys have issues. But let's take a look at, right, for Amos, if B is Amos Eaton, okay, actually, I'll run through the Amos Eaton one too. Okay, so for Amos Eaton, I'm going to say A equals Amos Eaton because I don't want to type Amos Eaton more than I have to. So Amos Eaton is a string. What we want to do is we want to, or maybe I'll use Y to be Amos Eaton so we don't get confused with our A's. Okay, so we have Y equals Amos Eaton. And now what what problem 2 is asking us to do is to, I'm supposed to do name. I like name being Neil deGrasse Tyson. Okay, so Y is Amos Eaton. you guys would have name. And what we want is we want to generate a string where each A has as many A's as there are entire A's in Amos Eaton. So we know that y.count shouldn't wash my hands. Every time I wash my hands, I can't use them anymore. They get all waterlogged. So if we want to know how many A's there are in Amos Eaton, we can do a y.count. So now what we want to do is we want to take each A in Amos Eaton and replace it by y.count, 2 times the character A, right? Because y.count times the character A will give us that many A's, right? So this generates the string we want to use as the replacement string. And now we can just do a y.replace. And what we want to replace is we want to replace each single A. And what we want to replace them with is the number of A's times the string A. So for Amos Eaton, this will give us Amos Eaton, right? And it doesn't matter how many A's we have if we set y to be something like, I don't know, aardvark. Probably not spelled correctly, but close enough. Or maybe even aardvark / anteater, right? That string actually has 2, 3, 4, 5 A's. So if we run the same code on that, that'll give us aardvark, anteater. Okay, so anyway, that's what we're trying to. That's what this piece of code will actually do, and it should be resilient to however many A's you want to put in it. We could even do something like y equals b and do the same thing, and that should just give us b. Okay. The second one we wanted to look at was Rensselaer Polytechnic Institute. So we will say y equals by the way, you can't graduate until you can spell this. And of course, that was not a spelling error. Okay, so what we're trying to do for this one is we're trying to replace all the E's with A's and all the A's with E's. So we want to do a y.replace. But the problem here is that if we do a y.replace E with A, right, then the next time through we'll replace right, we'll get something where there's all A's and no E's, and the next time through we're going to turn all of those A's into E's. So for this one we have to use a little bit of a trick, and the trick we use is to use something that we know isn't in the word. For this one we'll just assume we know that we know that 1 is not in y, so we can do that, right? That replaces all the E's with 1's. And now we're going to use the trick that I showed you before. This is the string that gets returned by this call. This is a string. So a string can have dot notation and another replace. So now now that we've replaced all the E's with 1's, we can replace all the A's with E's. And then we can replace all of the 1's. Well, we'll just do that first, right? So now we have all the A's replaced by E's, and all the E's that were originally there are still 1's, and we can just go through and continue to stack these and replace all the 1's that we artificially created with A's. Okay, so that's just kind of how to go through and do some of these string manipulations. Okay, I'm going to slap up a little bit of a screen here to help me figure out when I can quit or cut. Bum, 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 bum.